What we're now going to do is discuss what happens to the low mass stars as they shift around on the HR diagram and what physical properties are driving these various shifts. In this picture we see here, this isn't a nebula, it's in fact a red giant with this fascinating cloud of debris surrounding it. So, stars on the main sequence eventually runs out of helium to burn and it becomes a red giant. The surface temperature will decrease when it's a red giant, but because of the radius increasing, the swelling up, the luminosity is increasing. So that's this A part. You'll have what's called the helium flash. Triple alpha process begins. We're burning helium. We've gotten that electron degeneracy pressure was enough to start fusing helium atoms together. Then you'll enter what can be called a horizontal branch. Short branch here, we'll have another diagram where it's a little bit longer. But we call it a horizontal branch. Basically, the star becomes a little bit hotter. So it'll go a little bit hotter in this direction. Its luminosity stays about the same or decreases a little bit. And while we're on this horizontal branch phase of the star, helium is being fused into carbon or through another reaction chain into some oxygen in the core. Then eventually at the end, it becomes an asymptotic giant branch. The star will eventually run out of helium. No more helium to fuse, and so it swells up in size again. Luminosity increases. So let's go through each of these steps in a little more detail, step by step. All right. So, star is the main sequence, and it leaves the main sequence until the helium flash occurs. It's a red giant, that inert core, helium flash triggers, and now we're going to start going to a burning helium core. After we've gone through that helium flash, we reach this horizontal branch. All right. So our horizontal branch star looks more like a regular star. It went from red giant swell up to horizontal branch. It swells back down. The core itself, let's look at this. In the center, you've got this burning helium core surrounded by a hydrogen burning shell. And inside that helium, carbon and oxygen are starting to build up. We talked about the triple alpha process that's making the carbon. There is another fusion chain that can produce the oxygen. So the star is getting smaller and smaller and hotter. But eventually that helium runs out. There's no more helium in the core. So we now have a non-burning degenerate core of carbon surrounded by a helium burning shell. Surrounding that is a hydrogen burning shell. Surrounding that is the non-burning envelope. So you go from the inner side, core of carbon now, burning helium, burning hydrogen. And at this stage, this is the asymptotic giant branch, an AGB. And the star grows again, easily misconstrued as a red giant, right? So here's one diagram to stitch all of these pieces together, right? You have your main sequence star. So we're on the main sequence, and we're on a lower mass stars. That's the whole theme of this section. Run out of hydrogen, turn yourself into a red giant. You balloon in size, right? Balloon. And then when the helium flash occurs, you start going from an inert core of just helium atoms to burning. So you fall down here. The star shrinks in size, but gets hotter. It gets hotter because there's a lot more fusion happening in the core again. But eventually, so does the helium run out, just like the carbon. And now you've got this chain of helium surrounded by a hydrogen core. And you grow. You're this asymptotic giant branch, and you grow in size again until you run out of helium to burn. And at this stage, we are at the end of the low mass stars. Can't fuse beyond carbon and oxygen in the core. So you have this star that slowly becomes unstable. There's no more fusion reactions happening in that core. And what will eventually happen is that star will start to, I like to describe it as, burp up its outer layers. Specifically, we call it a nebula ejection. The outer layers just start to get pushed off of the star. And that's this long arc that we see in the HR diagram as it's done being an asymptotic giant branch star. And it will slowly cool off down into a white dwarf. So because of the star going past the AGB phase, it starts spitting out all of its excess materials. The energy holding the core nice and stable and even trying to gravitationally attract the outer layers is causing these destabilizations across the entirety of the star. And that's why it loses these outer layers. And these will now go back to actual astronomical pictures. These are what we're going to see when we talk about the planetary nebulas. Often they'll be ring-shaped. This one was called the butterfly. And it's this shell of just expanding gas that got launched off the upper layers of the stars. They'll often be gases that are just completely ionized, and the clouds themselves, they can last upwards of 50,000 years. After that, remember, every single one of these bright colors here is a little particle going away from the center, flying offwards. So after a couple thousand years, they'll have dispersed far enough away that there won't be so much as a nebula to associate with that former star. In the core, so this is the outer layers of what was that star, in the core will be left a white dwarf star. Here's the white dwarf surrounded by its nebula. The core, there is no fusion happening in these dwarf stars. This core is going to be very hot, but not very luminous. It'll have a mass between 0.6 the sun mass to a little bit like 1.5 times the sun's mass. And this is mainly carbon. Remember, the low mass stars, they cease being able to push matter together through fusion processes anymore at the level of carbon. So it's this very dense carbon core. And it was this very hot object, and it's just radiating all of its thermal energy away over time. It's cooling off slowly through the millions of years because it was a hot object just glowing in space. No more fusion to replace that missing energy. So the white dwarfs, as they get older and older, will become dimmer and dimmer. And all of our low mass stars are going to become white dwarfs, with the exception of what we'll say is our binary stars. Those going to have another chain that compounds the complexity here. But for a star, a lone low mass star, it's going to turn into a white dwarf and slowly cool off through the millennia to just a dim carbon nucleus.